Alright, we're closing out this section with the discussion of functions being equal up to a particular order, then talking about something which is actually like Taylor polynomials. By the way, for part, well, I'll talk about that later. So for A, suppose f is, so we need to prove an if and only if, so we'll start with forward. Suppose f is differentiable at A. So the first thing that we should do just to sort of get a feel for this exercise is figure out if, assuming this is true, then if f is differentiable, what are A0 and A1? And once you know that, not only can you do the forwards direction, but it also shows you how to go about the reverse direction. So g of x is going to be f of a plus f prime of a times x minus a. And this should look familiar because what is this? This is precisely the equation of a tangent line to f at a. If you work everything out. Because if you plug in, let's see here, do we even show this? Yeah, if you plug in g of a, well, the f prime term is going to drop out because you get a minus a, and so g of a is precisely f of a. And also, we're going to prove that also g prime of x is just going to be f prime of a. And so, yeah, this is a line through a line which passes through the point a comma f of a, which has the same slope as the derivative of f at a, and so it's a tangent line to f at a. And so it makes sense that this should be the function which is equal to f up to first order. That would be precisely the derivative. Okay, so then if we take the limit as h goes to 0 of f of a plus h minus g of a plus h over h, because here we're letting n be 1. So this is the limit as h goes to 0. So f of a plus h is there. Now g of a plus h is, let's see here, so we're subtracting f of a plus, no, f of a plus f prime of a times a plus h minus a over h. And we look at a plus h minus a and we say, aha, this is just h. And so this is the limit as h goes to 0 of f of a plus h minus f of a minus h times f prime of a over h. And we know that f is differentiable at a, and so that means that this is exactly equal to 0. So f, and I'll just say f equals g up to first order at a. Because this limit that we started with is 0, and that's what it means for them to be equal up to first order at a. Okay. Okay, yeah, okay. So, conversely, suppose f equals g up to first order, where g of x equals a0 plus a1 of x. So this tells us that 0 is the limit as h goes to 0 of f of a plus h. No, what? It should be x minus a here. So 0 equals the limit as h goes to 0 of f of a plus h minus g of a plus h over 0. We have this equality because we know from the get-go that it's equal up to first order. Why did I put over 0? Not only was that wrong, but of all the wrong things to write, I wrote the thing that's undefined. Anyways, maybe I was saying 0 as I was writing, and my brain was like, oh, guess we're going to write what we're saying. So the numerator, so this is f of a plus h minus a0 minus, and we have a1 times a plus h minus a. So that's a1h over h. So this limit is 0. So in particular, the numerator has to be 0. Particular, we have 0 is the limit as h goes to 0 of f of a plus h minus a0 minus a1h. And we can actually take this limit. So we can take the limit as h goes to 0 of f of a plus h. We can take that limit inside of f. Have we proven that? I don't think we have. But, okay, so little fact from real analysis that you'll learn in like Baby Rudin, Principles of Mathematical Analysis. If you have a continuous function, then you can take the limit inside the continuous function. So f is a function which is continuous at a. And why is it continuous at a? It's continuous at a because we proved in exercise 2-1 that a function which is differentiable at a is also continuous at a. So f, we are... Oh... We don't know that f is differentiable yet. That's what we're trying to prove. Okay. Alright, are we going to see if I can do this on the fly? Let's try it. So we have 0 is less than or equal to f of a plus h minus a0 minus a1h over norm of h. This is going to be less than epsilon for any, or this is going to be less than or equal to epsilon for any epsilon which is greater than 0. And so let's see here. So we have 0 is less than or equal to f of a plus b minus a0 minus a1h. So they're equal to epsilon times h. I am no longer convinced that this exercise is true. Because let's think about this. Suppose we have f is equal to this. Let's draw that a little nicer. And y is equal to this. And they meet here. So y is going to be x squared, is going to be, or f of x is going to be x squared. This is of course x and this is y. And then we've got this tangent line here. So now what we can do is suppose we have this. We take, so we'll have an open there. Perfect. And then at this point, f will take that value. And then we've got this tangent line through this point. So this is f and this is g. So this is g. So if we look at this, f and g, assuming that that if let's say this open circle that I have here were closed and that were a point on f, then this would just be f equals x squared, f of x equals x squared, and assuming, of course, that g is a tangent line at a particular point, then f will be equal to g, or then, yeah, f will be equal to g up to first order at this particular point. However, if we change the value of f at that point, then it's no longer true that if we change the value of f at that point, it's still true that f is equal to g up to first order, because when you take the limit as h goes to 0, you're not considering f of a. So this right here, this point where we have the discontinuity, is a. So if you've got that discontinuity there, then f and g are still equal up to first order at a, because when you take the limit, you're not considering the value of f at a. However, f is not differentiable at a because f is not continuous at a. So just because a function, f equals a linear function up to first order does not necessarily imply that the function is continuous. However, it should be true, and in fact we can prove it is true, that if f is continuous at a, then the two are equivalent. Then if we know that f is continuous at a, then it's true that if we know that f is continuous at a, then we know that differentiability of f at a is equivalent to being equal up to first order to a linear function. And let's prove that. So we have 0 is the limit as h goes to 0 of f of a plus h minus a0 minus a1h. And this is, well, I guess you could just use the definition of continuity to bring that limit on the inside. So this is f of a minus a0, and then the minus a1h, that will go to 0. So f of a, so a0 equals f of a. And that's what we need. So we need continuity of f, but then we get the desired result. All right? All right. Also, if we plug that into the original limit that we have 0 equals the limit as h goes to 0 of f of a plus h minus f of a minus a1h over h. And so, by the definition of differentiability, f is differentiable at a, and f prime of a equals a1. Alright, so now that's what we need for a. We proved both directions. We had to add an extra condition that wasn't mentioned, but oh well, not a big deal. Alright, part B. If f has n derivatives at a, show that f and the function g defined by g is just this function, our equal up to nth order at A. And so, yeah, first of all, if you look at this, you should recognize this if you've taken like Calc 2. This is just a Taylor polynomial of degree n of G at A. And so this is sort of a neat result about Taylor polynomials. And also the textbook has a hint for this, and it says to use L'Hopital. And I really don't like that, because what is L'Hopital? We haven't proved L'Hopital's theorem, so we technically can't use it. I mean, even if we look at the next section, the first thing we do in the next section is we prove the chain rule. And so if we're going ahead and proving all of these things, we need to prove L'Hopital's rule before we can use it. But this book seems like it's like sort of like an awkward transition from knowing techniques in calculus and not having the proofs to proving all of the techniques that you normally use in calculus. So L'Hopital is one of those things that people typically know by this point. It's typically taught in like Calc 1, although like I took AP Calc in high school and we didn't have time to cover it. I just took like AB. But yeah, I remember like going to college, and then eventually I took Calc 2, and there was one day like early on, first couple weeks, where the professor uses L'Hopital, and I was like, what is that? Do I need to know how to do that? And the professor was like, yeah, you should know that. So I went on YouTube, and I looked up some of the Khan Academy videos before they had their own website, back when it was all on YouTube. And I looked up his video on it, and I learned it. And now I'm making YouTube videos. So that's cool. These things, I think these are really good learning tools. But anyways, we don't know, we haven't proven L'Hopital's rule yet, so I think it's weird to have to use it in an exercise. But it also allows us to actually, if we assume L'Hopital's rule, then it allows us to do something neat. You do have to be a little careful when you're doing that kind of thing, like assuming that this tool is valid, because you can get into circular arguments, which is not ideal. But yeah, here it's probably fine. And then eventually, if you get to a textbook like, as I keep talking about, Baby Rudin, you will eventually get to a point where you are actually proving all of these things that you're doing. So anyways, let's prove B. Finally, we have, and now I sort of just go through and prove this. Here, I'll write out one line. Let me as h goes to 0. We have f of a plus h. So this is interesting, because I went through this and I actually struggled with this for a little bit, and I was like, how does this work? And then I just tried to do it, and it just works. So not only is the hint like it has you use or it asks you to use L'Hopital, but it asks you to do it in a way that makes it less useful, or makes it in a way that's slightly different from what you have to do in the exercise. So I think it's a little weird. Anyways, so we're taking this limit. This limit needs to be 0 for f and g to be equal up to nth order. So now what we're going to do is we're going to use L'Hopital's rule, which says that if we look at this limit, alright, so I went back and I was like, oh, this is broken, but then I realized that's not. Because I remembered that when we're taking the limit as h goes to 0, this sum over here, the first term is I equals 0. So the h doesn't even matter. So for I equals 1 to n, when you take the limit as h goes to 0, this numerator becomes, like, you'll have h to some positive power, and so that will go to 0. However, for the I equals 0 case, all we have is f of a. So when we take h to 0, on the top we get f of a plus h, which of course goes to f of a, minus f of a. And of course that's equal to 0. And in the denominator, we have h to the n, and that's obviously going to go to 0. And so you can take the derivative. And when you take the derivative, you'll end up with f prime of a plus h minus the sum from, let's see here, the sum itself might change a little bit because the I equals 0 term drops out, so it's going to be the sum from I equals 1 to n of something over n times h to the power of n minus 1. And there, if you take h to 0, denominator you get 0 again. In the numerator, the f prime of a plus h will go to f of a. And then for the sum, most of the terms will drop out. The only one that will remain is, let's see here. So when for the I equals 1 term that we started in the beginning with, we had, so that was just f of a times h. And when you take the derivative, you get f prime of a. So that will cancel with the f prime of a that we got as the limit of f prime of a plus h. And so the numerator will be 0 again. So I suppose this would be best done as like an induction argument, but you can sort of see, or you can prove, that you can use L'Hopital's rule continuously because this will be of the form 0 over 0. So what we're going to do is we're going to take n minus 1 derivatives by L'Hopital's rule. We're going to take n minus 1 derivatives, and so here we'll end up with the n minus 1 derivative of f at a plus h minus, and then if we look at the sum, if I is less than n, if I is less than n minus 1, then when you take n minus 1 derivatives, the h term is eventually going to go to 0. So all of those terms are going to drop out. The only terms that will remain are the terms corresponding to I equals n minus 1 and I equals n. For the I equals n minus 1, let's see here, the n minus 1 derivative of f at a over n minus 1 factorial, that's going to stay. However, h to the power of n minus 1, you take n minus 1 derivatives, and that's going to become n minus 1 factorial. And that will cancel with the n minus 1 factorial that's in the denominator of this particular term. And so all that will be left over from that term is f of n minus 1 of a. And so that's the n minus 1 term. For the n term, we will have the nth derivative of f at a over n factorial, and then we'll take n minus 1 derivatives of h to the power of n. And that's going to give us n factorial. Again, the reason that we get n minus 1 factorial for the previous one and n factorial for this one, it's because in one of them you end up multiplying for h to the n minus 1, you end up multiplying by 1, because when you take the derivative of h, you just get 1. And so you get 1 times 2 times 3 times 4 times, all the way up to n minus 1. However, for this one, since you're only taking n minus 1 derivatives, you only go down to 2, and you remain with a factor of h to the 1. So you technically get 2 times 3 times 4 times all the way up to n, but that's equal to n factorial because the 1 doesn't matter. So that's why you get factorials in both of these terms. It's because the 1 in the factorial doesn't matter. So anyways, we'll be left with nth derivative of f at a. The n factorials will cancel and we'll just be left with h. And this is being divided by, okay, now when you take n derivatives of h, you get n factorial times h, like we just talked about. And so this is equal to 1, we can factor out the 1 over n factorial because that's just a constant. And then we get the limit as h goes to 0 of fn minus 1a plus h minus fn minus 1a minus fna of times h over h. And that by definition is, or that is 0 because f is n times differentiable at a. So the n minus 1 derivative of f at a is, so the n minus 1 derivative of f is itself differentiable at a, and its derivative is the nth derivative of f at a. And so what that means is that this limit that we see here, if you remove the n factorial, must be precisely 0. So this limit equals 0. And so that means that this limit that we began with is equal to 0. And so, but the limit that we began with is precisely the limit that needs to be 0 in order for f to be equal to g up to nth order. And so there we go. And by the way, note here that we needed f to have f needs to have derivatives 1 through n at a, because first of all, this sum of the nth derivative, or the sum of the ith derivative of f at a for I equals 0 to n, that isn't even defined unless f is differentiable, or f is n times differentiable at a. But furthermore, we particularly needed that final derivative in order to get this limit to be equal to 0. But yeah, that's how we can use L'Hopital to prove that f and the nth degree Taylor polynomial of f at a are equal up to nth order. And so now we are done with this exercise.